Hi, welcome to the second part of lecture 3. In this in this part of the lecture, we're going to talk about how to do the matrix factorization model, the one that you are doing for your homework or you just finished doing for your homework for in PyTorch. You're going to see how easy is everything in PyTorch as opposed to the Python code that you had to write. So first, I am going to um, download the dataset that you guys already have. So I have it here, and so I have some user IDs, movie IDs, rating, and timestamp. The first thing I'm gonna do is I'm gonna get this into a pandas data frame, so I have the same data. The first thing I need to do is that I need to take my training data and divide into training and validation. When you have time series data, which is in this case you have the timestamp, the right thing to do is to take as validation set the latest data. So what I have done here is I have taken the 80th quantile of the timestamp values, and I'm gonna use the latest data for validation and the earliest data for training. So that's basically a simple way to do this. So this is my validation data and my training data. So I have some IDs here. I have 522 users in this dataset, but not all of the IDs. So basically I need IDs to be between 0 and 521. So, and right now they are not continuous values, integers. So what I'm gonna do is that first thing I'm gonna do is I'm going to compute a mapping between the all IDs and new IDs. So you can see here I have the all IDs and the new IDs. Okay, good. So I have that, and I am gonna do the same for the movies, so which I have it somewhere down there. So and then what I'm gonna do is that I am going to use the apply function to could basically change the user ID with these new IDs that I created. Okay, so I'm gonna do that. So you see now my user IDs, they start at 0. Okay, and I'm gonna do the same for validation, but then if I find an ID that I've never seen before, and I'm gonna use a -1, and then I'll get rid of that, because if I don't have that ID in training, I am not gonna be able to predict on that ID. Okay, so I do the same. I apply my change of my mapping between the old IDs and the new IDs, and yeah, I'll tell you a bit later why I need these IDs to be between 0 and the number of users -1. So and then I am going to get rid of the user IDs that were -1, because those user IDs were not on the training data. Okay, so I did that. Now I do the same thing for movies. Okay, so I go ahead and get new IDs for movies, and then all is good. The movies IDs, they start at 0. Okay, perfect. So that's kind of a pre-processing that you guys also had to do for your homework. So now I want to talk about something called the embedding layer. And the embedding layer is basically a type of layer that people use in neural networks. The embedding layer takes, in this case, is going to take every item or every user and convert that into a vector of a fixed length, k. Okay, these vectors are going to be parameters of our model. This is the UI and VJ vectors that we have been using in a matrix factorization model. And ideally, these embeddings will capture the properties of the data, and it will place similar users close together to other users in the embedding space, other similar users in the embedding space. And similarly, it's going to place items that are similar into similar vectors in the embedding space. Okay, so let's see how this layer works. So this layer, a way to think about this layer is that this layer is just kind of a matrix so in one hand we have the number, in the rows we have the number of users, and in the columns we have a k, which is basically what's the length of your vector. So here in particular we have in this very small example, for example, we say, well, we have this embedding layer, then we have 10 users, and the embedding size, that's how we call this k, the embedding size is going to be 3. Okay, and again, these are numbers, like these are vectors, they all start random. Okay, and they are going to be optimized with them, you know, when we feed our model, these numbers are going to change and they're going to get optimized. Okay, so one thing that we can do is that given a set of IDs, for example, this is a list of IDs 1, 0, 1, 4, 5, 1, we can look up the current values of these vectors. And notice that I have the user 1 3 times here, right? So is the first one is user 1, the second one is user 0, the third one is user 1 again. And if you notice that I repeat the same vector 3 times, the first vector, the first row, the row number 3, and the last row are the same because they correspond to the embedding of user 1. Okay, so basically, in a way to think about this is that the embedding is a matrix in which I can look up these vectors that correspond to particular IDs that I need. Okay, so when I need the ID of user 1, I'll look up the ID of user 1, and I will look up like the vector corresponding to the user 1. If I need the vector for user 10, I do a lookup and I get a vector for user 10. Okay, and then I'm gonna go and modify these vectors as I train my model with data. Okay, so let's talk about the matrix factorization model that we have been talking about in class. Okay, and this is my model here. If you remember in the previous lecture, in the previous video, we talked about how to define models in PyTorch. So here we have the init, and if you remember, in the init is where we define all the parameters of this model. So this model has basically 2 layers. It has the user embedding layer, okay, and when we call a user embedding, we basically say, well, give me the number of users you have and the embedding size that you want. And for an item embedding, give me the number of items you have and the embedding size. Now, if you don't have the users going from 0 to the number of users minus 1, when you will call, hey, give me this particular user, if the ID is over the number of users, you're gonna get an error. So that's why I needed to do a mapping to the user ID to 0 to the number of users minus 1, so that this code would kind of work. So when you try to look up a particular vector, that vector exists. Okay. So then after I initialize my vectors here, after I initialize my vectors, these vectors are initialized in a particular way. So there are different ways to initialize vectors in PyTorch, but they are by default initialized. And for this particular model, I found that it's much better if you initialize these vectors with positive small numbers rather than initializing them in the way PyTorch initializes their vectors. So I am re-initializing these vectors with basically positive small weights. When I do this, the algorithm converges, and if I don't do that, sometimes it does and sometimes it doesn't. But you guys can go and try. So you just have to comment these two lines and see what happens, right? So in many of the models in PyTorch, you are not going to have to reinitialize the vectors. I'm doing it here because it just works better this way. Okay. And then after that, we want to write our forward. Okay. I'm going to tell you what this is doing, and then I am going to show you exactly why this works. Okay. So the forward takes a vector u and a vector v. U, remember, is users, and v are items. Now u and v here are IDs, the IDs of users and the IDs of items. Okay, I am gonna look up the first thing I do, I look up the vectors for a list of users. Then I look up the vectors for a list of items. And then I'll convince you later that what I have here is dot products between user vectors and item vectors. Okay, so let's debug this model. Let's take a little bit of a tiny amount of data and let's make sure that you guys agree with me that this is the metrics factorization model we have been talking about. Okay, so I have a little data set here of user, movies, and ratings. Okay, so how many unique users I have? Well, I have 5 unique users. How many unique movies I have? Well, in here I have 4 unique movies, right? So I define the number of users are 5, the number of items as 4, and then embedding size, let's just put 3. This is a very small example, so let's just put 3. So the first thing I do is that I initialize 2 embeddings, okay? The second thing I do is that so one thing that happens is that in order to look up, okay, so let me actually show you here what I have. So these are my users. Okay, so this is my list of users in the same way I see them here. Okay. And then I have my items. In the same way I see them in this matrix here. Okay. Now, the next thing I do is that I'm going to look up the vectors of all of these users and all of these items. So what do? I do this. I say u is user embedding in users. In order to do that, I had to convert these NumPy arrays into tensors of type long. And that's just the way it works. So for you to be able to use an embedding matrix, the numbers that you are using needs to be of type long. Otherwise, you're going to get an error. Okay, and this is something that you have to know. So basically, yeah. So basically, what I'm doing here is that I'm looking up the vector for each of these users. Notice that I have first user 0, then user 0, then user 1, then user 1, and you're gonna see that the first and the second vectors are identical because they correspond to user 0, and then the third and the fourth vector are identical because they correspond to user 1, and so on, right? So you have u and I have v, and v is similar, right? So what happens if I do u dot v? So this is element wise. So basically, let me actually, guys, let me so what am I trying to do here? So what I'm trying to do here is that I have u and I have v. To be able to have a prediction, I need to do a dot product between this vector here and that vector here, okay? And then a dot product between these and that, and so on. That's how I get predictions, right? That's how I can break predictions, and then I am going to compare the predictions to the ratings I have in here. So that's what I'm doing, right? But I'm trying to do this in a way that is in a vectorized way. So I don't want a for loop because that will take a lot of time. So a key for doing all of these operation fast is to do them in a vectorized way, avoiding for loops or anything like that. So one way to do that, and you guys could find a different way, is that we can find, if we multiply u and v, we get an element-wise multiplication. So if you remember what is a dot product is element-wise multiplication, and then you sum everything, right? So that's what I'm doing here. So I am doing this element-wise multiplication and then sum. To the sum, you have to say sum in 1 and not in 0. How you figured out that this is the right sum? Well, we know that in this case you need to get like 1, 2, 3, 4, 5, 6 values, right? So if you sum the wrong way, you're gonna get 3 values because you're gonna sum per row instead of per column. Okay, so that's how you know. So what I'm showing you here, this little process, is what I do every time that I need to figure out a model. Okay, so I do this, like I take a little bit of data and I try a little bit until I get what I want. In this case, we wanted a dot product. Well, I am hoping that I convince you that this is the way to get the dot products. So the inputs are the IDs, you do lookups to get the vectors, and then this is the way to do a dot product, and that's your prediction. And again, every time that in PyTorch we have a model, we're gonna pass a batch of data. So we're not passing one observation, we're passing a batch of observations. So we wanna make operations that work for a batch of data. And this works for a batch of data. So a batch is just a subset of the observations we have, okay? So, okay, so I convinced you that this is, now let me show you the training loop. So the training loop is gonna be pretty similar to what you guys have seen before, except for a couple of things that I will show you here. So this is a function that takes a model, the number of epochs. Remember, number of epochs is how many times you wanna go through the whole data. The learning rate and weight decay. And weight decay is pretty much the same as L2 regularization. So it's that lambda that you put in front of the L2 regularization. So the first thing I do is that I create an optimizer. And as I told you before, in this case, I'm using Adam. You can use Adam W or whichever one you want, right? Stochastic gradient descent with momentum, like anything you want. So basically, so I created my optimizer, okay? And then I go through a loop for the number of epochs. I do model train, just to tell my model that it is on the training mode. I have to convert my users and items as type long. If I was doing this on a GPU, I would have to put .CUDA here. That's why I left it there, just in case you guys are gonna run something on a GPU. And then I am turning my ratings into floats, torch tensors that are type float, okay? I am gonna send the users and items to my model to get a prediction. So that y hat is my prediction. I am going to define a loss. It's the MSE loss because that's kind of what we are training. Okay. Notice that in the way we're doing this, we are not constructing a huge matrix at any time, basically, because our gradients are gonna be computed by PyTorch. So we don't need to worry about that, basically. So So this is the beauty of this. So you just say, hey, this is my loss. This is my MSC loss. Then you have to basically put the gradients to 0, as I told you before. We do loss talk backwards. We do optimizer.step. Then I have a function I'll show you in a second that computes the loss for the validation set, and then I print loss for validation and testing. Okay, so that is my training loop. My validation, so I have a validation loop that basically what it does is compute, is very similar, except that you put the model in model.eval mode, and you're just computing the loss with respect to the validation data. Okay, I like to have them in different functions, but you guys could have all in the same function. And then, I define my model. This is the number of users I have, the number of items, the embedding size, which is a hyperparameter. If I was on a GPU, I would put here .CUDA to the model. And then I train my model. Oh, wow, what is this? Something is happening here. Index is out of range. And this is because most likely the number of users and number of items is wrong. So let me actually, because we were doing this. So let me actually go and update that. So yeah, sorry about that. I was playing with those. So I have to compute my number of users and number of items, and where do I have that? So okay, so let me user IDs here. Yeah, so I think what happened is that I need to restart this. Yeah, let me see, number of users. Yeah, it's not 5, right? So basically, that's actually this is a pretty good. So what it's telling me is index is out of range because I define an embedding with 5 users. I have 552 users actually. So that's the type of error you get when your embedding has the wrong size, right? The wrong number of users and number of items. Okay, so the lookup fails, right? So now this is actually a good example. So I have 522 users, and let's look up the number of items we have, which we had computed also right here. Okay, so hopefully this will fix the issue. So yeah, so let's see how many items we have. Okay, perfect. So we have 7,867 items. So let's reinitialize this model and let's run it. Okay, so things are going well. So guys, I don't know if you see that this learning rate sometimes is going up and down. So even the training loss goes down, but then at some point it goes up again. And this happens a lot when my learning rate is a bit high, right? So let's see what happens if I go I don't know. So let's still put a high learning rate, see what happens. So I just initialized my model. So this is important for you guys. Oh, wow. So still kind of going up and down. So yeah, up and down, training loss. So well, let's just then, so again, if you want to reinitialize the model, you need to actually kind of do that. Okay, so and then okay, so I see. So okay, so that's going down more nicely. You see, it's not going down as fast as the previous one, but it's not going up and down as much. On the other hand, let's actually go back to see what happens if I do this again. So I initialize again. You know what? I'm gonna keep this because it went down, up and down, but it didn't diverge. And I like that it kind of got to kind of a nice value at the end. So again, you have to play this a little bit, try to play it to see what happens. Hopefully now when I keep training, it's a little bit more stable. So let's keep training and see what happens. So now my training loss is going down, it's just more stable. So anyways, this is how you find learning rates. In a way, there is no real way of understanding what is a good learning rate. So I would start with the biggest value that doesn't oscillate that much, or at least doesn't diverge, basically. Because if you put a really high learning rate in here, let's just do it. Let's just put it 2 and see what happens. So I initialize my model again, and let's put a kind of a learning rate of 2. So you see what is happening? This is diverging. So you don't want that. That's just very, very high. So let's just kind of start again with my 0.1 learning rate, and because you just want this to go down mostly, or at least mostly go down, the training loss. The validation loss is a bit different, because the validation loss is trying to understand how well you are generalizing to the training data. So that could go up and down, because that is not what you are trying to optimize. But the training loss should go down, basically, most of the time. So let's do the second one. And let's keep going. Okay, so it seems that maybe we can play some tricks and get this to train a bit better, but this is what we got so far. So let's talk about a slightly more complicated model. So suppose that now, instead of just having the model to be a dot product between UI times VJ, which is the vector for the user, and a vector for an item, we could have a bias. So we can have a number for each user, which is the bias for the user. It's like when you're doing regression, you have like A times X plus B. That B is a bias, right? So it's a number. So here what we're gonna do is that we're gonna have a number per user. And the idea is the following. Some users maybe like to rate higher than others, right? So maybe there is a bias. The user itself has a bias for saying, you know, I'm a nice person. I don't like to give a 1 to anything. So I'm gonna do 3, 4, 5s, right? If I don't like something, I'm gonna give it a 3, right? And maybe there are users that are the opposite. They basically say, you know what, I just never like anything, and the maximum I'm gonna give is a 3, and I'm gonna do 1, 2, 3, right? So that's what this number is gonna capture. It's gonna capture some of the bias that user may have, up or down, right? And then you can say similarly that maybe some items are just better than other items. So maybe an item may have a bias. It may be just basically just better. So intrinsically, you're just gonna give it just higher values. So we can then also have a bias for each item, right? And this is just a different model. This model is just have more parameters than the previous model. So yeah, so that's it. So and how do I do this? So basically, you see I have now 4 embedding layers instead of 2. One embedding that goes from the number of users to the embedding size. That's basically the embedding layer for the users. Then I have an embedding layer for the bias. It goes from the number of users to 1 because I have one number per user. And similarly, I have an embedding matrix for the items and a bias for the items. And then I also initialize them. And then the forward is similar. But you can try to figure out how I got to this equation here, but hopefully it's gonna be clear. Okay, so I have this model, and I initialize my model, and I also kind of train it, and we will see, in principle we will think that this model that has more parameters should be able to fit better than the previous model, but that's maybe sometimes not the case, so we'll see. Okay, so let me try a couple of more times. Also notice that every time you retrain a model, you're retraining a different version of this model, because this model is getting initialized randomly. So the initialization matters a little bit. So you're not going to have exactly the same answer every time you run a model, except if we fix the seed for the model. Okay, so we got some validation of 0.85, 86, right? And over here we have a validation set of 0.85. Actually, this new model didn't really improve our predictions that much, but we tried, right? Okay guys, so this is what I have for now. Yeah, see you in the next lecture.